Dear friends, welcome back. In our previous lecture, we are talking about wing planform geometry and how to find the mean aerodynamic chord and the aerodynamic center for a given wing, right? So, this is consider a fuselage reference line. Assume that this is a wing, a semi-span of a wing, and you have a root chord and you have tip chord. And this be B by 2, which is semi-span. B by 2. So we have defined some non-dimensional parameters called aspect ratio here, which is B square by S, where S is the wing planform area. And lambda is the taper ratio, the aspect ratio, and taper ratio. Lambda is equals to Ct by Cr. Where Cr is the root chord and Ct is the tip chord. And we also witnessed that for a rectangular wing, aspect ratio is B by C, and the respective surface area will be planform area will be B into C bar. And for rectangular wing, taper ratio is 1 because Ct is equals to Cr for a rectangular. Okay, so this is for rectangular wing. And for a triangular wing, what we have is aspect ratio is equals to B square by S, and area of a triangle is half into span into height is Cr, right? And lambda taper ratio is Ct by Cr, which is 0 for a proper triangular wing. Okay. Now, the main important thing is, at a later stage, we'll represent the entire wing by means of mean aerodynamic chord and the aerodynamic center, with the respective forces and moments acting at the aerodynamic center. So while performing stability analysis and while sizing the wing, and say for this particular wing, what should be the corresponding tail size, right? If you are designing a conventional aircraft, right? So during that process, we represent both wing and tail by means of this mean aerodynamic chord. So how do you find mean aerodynamic chord? MAC is C bar is equals to 2/3 Cr into 1 plus lambda square by 1 plus lambda, right? That gives mean aerodynamic chord. So this is your C bar, and the Y location of this C bar, YMAC, is given by B by 6 into 1 plus 2 lambda by 1 plus lambda. Okay. So consider a rectangular wing. What will be the C bar? What is lambda? Lambda is 1 in that case. So for rectangular wing, C bar is equals to 2/3 into CR is C. For a rectangular wing, we have lambda is equals to 1. Substitute 1 in this equation. So what you have, C bar is equals to C, right? Which is the CR and CT in that case. What about for a triangular wing? 2/3 of the root CR, root chord, right? So for a triangular wing, it is C bar is equals to 2/3 of C. With this mean aerodynamic chord, how to find the aerodynamic center? So aerodynamic center of wing. So we are talking about a subsonic UAV, right? So we can safely assume this C bar, this AC aerodynamic center will be approximately at 25% of mean aerodynamic chord, right? So once you know the mean aerodynamic chord, you can project this mean aerodynamic chord onto your root chord, right? You can actually project this mean aerodynamic chord onto the root chord and take 25% of this root mean aerodynamic chord to locate the aerodynamic center. So since you know the root chord, so say this is your root chord, and you know C bar, right? Say this is your C bar. So what you can do is you can find what is your mean aerodynamic chord x of AC that represents aerodynamic center of the with respect to the leading edge of this root chord, right? XAC is equals to, so XAC is equals to CR minus C bar plus 0.25 times of C bar. This is C bar, CR minus 0.75 C bar. So this is the relation with which you can calculate or you can locate your aerodynamic center with respect to leading edge of this root chord. So we are also talking about span-wise distribution of aerofoils, right? So this is my wing. Now let us say this is my CR or root chord, the line connecting the leading edge and the trailing edge of the root. Say this is my center line or fuselage reference line. Okay. Now consider a span-wise location Y, or say the tip. Consider the tip aerofoil, which is at a distance b/2 with respect to this root chord, or from the fuselage reference line. Okay. Now, if the tip aerofoil, let us say I project this tip aerofoil onto the root. If this tip aerofoil, which is present here, say, okay, if the chord of this tip aerofoil is above the chord of this root aerofoil, right, then we call it as positive geometric twist. say if this tip aerofoil is below this, if the chord of the tip aerofoil, if it is oriented in this direction, say if this is your tip aerofoil, so say if this is your chord, and say if the chord is below this root chord, right? If the angle is below the root chord, then you call this as negative twist. Negative twist. Okay. So this is basically you are giving a physical rotation to an aerofoil at the tip. Right? You can have a constant twist as well as variable twist wings. Right? Okay. Now say at a span-wise location. Okay, this is b by 2. Say let that location be y. Right. So at this location, say if the shape of this aerofoil is different compared to the shape of the root chord aerofoil. That means say this is a cambered aerofoil, and at that particular location I started using a symmetric aerofoil. Right. So although the chord line of the aerofoil present at this location is in the same plane as the chord line of this root chord, right? So but the profile changes because I am changing the aerofoil, and the corresponding upper and lower coordinates of this particular aerofoil are different compared to that of the aerofoil that we have used at the root, right? So because of this, although there is no physical rotation that is given, because of the change in the aerofoil, the wing looks twisted, right? You call it as aerodynamic twist, right? Right. So aerodynamic twist is to change the lifting properties along the span-wise location of this wing, right? Let's look at a wing here. It's a rectangular wing. In our previous lecture, we saw a tapered wing about the mid chord, and in this case, it's a pure rectangular wing. You can see. So this is the side view you are looking at, right? So these particular structural members are known as ribs, and you have spars here, right? So this is the skeleton of a typical wing. It's about a meter span. Right. So let us consider a rectangular wing. Okay. Let us consider a rectangular wing. Now, at each and every location you have aerofoils. Let us say there is no twist and there is no geometric as well as aerodynamic twist. So we have same aerofoils oriented in a similar way. Like the orientation of this is exactly what we have it as root chord, right? That means the chord of each aerofoil lies in the same plane. Okay. Now we witnessed earlier like there will be pressure distribution on aerofoil, right? Say what will be the pressure distribution here, say when there is flow, you have pressure distribution here, right? And say on this wing again you will have a similar pressure distribution because the chord is not changed, right? So at each and every location you have similar pressure distribution. right? Now you will have a resultant component of this at each and every point. Right? Here say maybe somewhere here, somewhere here. Since it is not tapered, it will be lying. It will lie on a same perpendicular plane to the wingspan, right? Now, if you look at from this direction or from here, what you can say is, say if this is my wing, for a rectangular wing, the lift distribution will be something like this. So we can also talk about lift distribution along the span-wise location. Right? So we have lift distribution at a particular cross section, that is because of the flow or airfoil, right? And we can talk about lift distribution along the span-wise location, right? And it mainly depends upon the plan form of the wing, shape of this wing, right? Now, see, don't you see, these are the tip, this is the tip. You'll have a wing symmetric about this fuselage reference line, say this is your FRL, this is your FRL, okay, fuselage reference line, right. So you'll have a symmetric wing and with the symmetric distribution. But what happens at these tips? So this is the tip of this wing, right? And you have a tip aerofoil there. And similar to that of any other aerofoil along the span, this tip aerofoil will also have this pressure distribution, right? So you know you have a greater suction on an aerofoil, you have a greater suction on the upper surface compared to that of lower surface. That means you can say low pressure on upper surface and higher pressure on bottom surface. So due to what happens, will there be a flow that, so there is a sudden ending, right? The wing is ending abruptly here. Now what happens at that particular point, the flow from the bottom surface will try to curl towards the upper surface at that particular location. Now when you look at the tips, right, which are the extremes of the wing, so say this is my fuselage reference line, okay, and near the tips, when there is a flow, so on this aerofoil as well, there is a greater suction on the upper surface and comparatively lesser suction on the lower surface, right? So which means there is a higher pressure on the lower surface and lower pressure on the upper surface. Now since this wing is abruptly ending, what happens, the flow near the tips, right, will try to curl from the bottom surface to higher surface, top surface, right? That is from higher pressure to lower pressure regime, right? So this curling will actually affect the span-wise flow, right? Will actually induce the span-wise flow. Ideally, the flow has to be along the chord, right? But this curling, due to the finiteness of due to a finite wing, will induce a span-wise component of velocity to this flow, right? So how to model this? How to model this phenomenon? So lifting line theory. So lifting line theory talks about lift distribution along the span of a wing, right? So this whole setup, like the wing and the trailing edge, trailing vertexes, are replaced by a bound vortex and associated with two trailing vertex. So how the flow will be at this particular tip? So the wing is replaced by a bound vortex, and at the tip, what happens? How the flow direction of the flow will be? From bottom to top, right? The flow velocity direction will be from bottom to top. in counterclockwise direction. So at this tip, it will be along the clock. It will be in the clockwise direction, right? So and these two vertices are connected by a starting vertex. So this entire vortex architecture that represents the lift distribution on the wing is known as horseshoe vortex, right? Horseshoe vortex. So this horseshoe vortex is used to model the lift along the span, right? Or model the lift of a finite wing here. This vertex architecture, right? So let us consider this bound vertex, what it is going to, how this is going to influence the flow over the wing, right? Let us take the side view here. So this bound vertex will induce an upwash ahead of the wing and downwash behind the wing. So assume that it tries to push the flow down behind the wing and push the flow up ahead of the wing, right? Makes the flow move up, right? Whereas this trailing vertex will create a downwash along the span-wise, throughout the span of the wing, right? So this combination, this upwash and downwash combination this upwash and downwash combination will result in a flow field something similar to this, right? So this alters the local angle of attack at each and every span-wise location, right? Now what happens is, let us consider a span-wise location along the wing. Let this be the angle of attack, airfoil, which is at an angle of attack V infinity. This is a direction of the actual flow, right? Overall flow. Now, what happens is, due to this downwash, so effectively this angle of attack decreases, right? There is something called induced angle of attack. So these two are similar, right? This is the local velocity, direction of local velocity, direction in which, and this will be your, say this is my actual angle of attack and this is my effective angle of attack or the local angle of attack, right? So this is this quantity, this is the downwash, and both are same, these two are same, right? So this is the downwash which is affecting the flow at a particular span-wise location, right? So that causes an induced angle of attack, alpha I. Now, so the local lift will be perpendicular to this. So the actual lift direction, say, this is my lift of the overall aircraft, right? Overall wing, which is perpendicular to the free stream velocity, right? But the local velocity is at an angle alpha I with respect to this free stream velocity, right? So the local lift will be perpendicular to V infinity local. So this will be the component. Say this is the local velocity and the corresponding local lift, alpha lift at that particular location, local lift, right? And this is your drag, right, which is acting along V infinity. Now this local lift has a contribution along the actual lift of the aircraft or the overall lift of the aircraft, as well as along the drag, overall drag of this aircraft. So what is this CDI, let us say, is the coefficient of induced drag, right, is equals to CL is the coefficient of lift at that location, right, into, so this is your alpha I, right, this into sine of alpha I. Since this induced angles will be very small, what you can assume is CL into alpha I, induced angle of attack. Okay? Induced angle of attack is contributing induced drag, right? So the lift generated here is also contributing towards drag, right? This is the penalty that we are paying, that we'll discuss very soon. CDI is equals to CL into alpha I, right? So according to this lifting line theory, this alpha I is equals to CL by pi E AR. Alpha I, or the lift and induced angle of attack, is related by alpha I is equals to CL by pi E AR, where E is the Ostwald's efficiency factor. Okay, and AR is the aspect ratio, which is B square by S, right? Now substitute this alpha I here in this induced drag. So CDI is equals to CL square divided by pi E AR. So the lift also contributes towards induced drag, right, due to the finite aspect ratio. So for a 2D wing, it is infinite, aspect ratio is infinite, so induced drag is almost negligible there. What we need to talk is, what is drag? We already defined, it's a component of resultant aerodynamic force which is acting along the free stream velocity, right? So say this is your aircraft. This is your aircraft, and you have thrust, which helps the aircraft to move at the required velocity, and you have weight, and say this is your V infinity, and say this is your fuselage reference line or the reference line, and this is your alpha. What you have is lift and drag as aerodynamic forces. Now this drag is a component of resultant aerodynamic force acting along this V infinity, right, or parallel to free stream, which is defined as half rho V square S into CD, right? So this is the dynamic pressure times the planform area and non-dimensional drag coefficient. So this CD is given as CD naught, can be expressed as CD naught plus K CL square, which is known as drag polar. Drag polar. Right? So this KCL square is nothing but CDI, where K is equals to where K is equals to 1 by pi E air. So here Cl square by pi E air, right? So CD is a summation of something called profile drag or lift independent drag and lift induced drag. So you call induced drag. Okay. So this is how the induced drag is related, right, with respect to with CL and the aspect ratio. Yeah. We'll look at what is this Ostwald's efficiency factor. We'll come back to that. Right. So this profile drag again is due to skin friction. Since we are moving in a fluid and fluid is in contact with the surface of or the skin of this aerofoil or the exposed surface of the aircraft, so it has some fluid friction. So that is known as skin friction. Skin friction drag plus pressure drag due to flow separation. So pressure drag due to flow separation, right? And as you go to higher velocities, there is something also called wave drag, right? That comes into picture. Yeah. And in this lectures we are going to discuss only about low speed UAVs. So there is no need for us to discuss much about this wave drag here, right? So you have CD naught plus CL square by pi E air, right? So these are profile drag coefficient. In fact, please add this induced drag coefficient. So these induced drag and profile drag coefficients multiplied by half rho v square s will give you the corresponding profile drag and induced drag, right? Okay. So CD or drag is equals to half rho v square s into CD is equals to half rho v infinity square s into CD naught plus K CL square is equals to half rho v infinity square s into CD naught plus half rho v infinity square s K into CL square, right? So this particular term is profile drag plus induced drag. Now we have expressed CD as a function of CL, right? Here CD is equal to CD naught plus KCL square. Now we can see it's a quadratic function. Now let us plot CD with CL. At CL is equals to 0, you have something called CD naught typically this is how CD versus CL plot look like, right? So there is something also called drag bucket, right, where the CD value almost remains constant for a range of CL values, right? So that particular regime for which the CD remains constant with CL is known as drag bucket. So since we mentioned drag bucket, it is worth discussing about various aerofoils, various series of aerofoils, right? So it may not exist explicitly for all the aerofoils, but there are some aerofoils called laminar series aerofoils where you can see such a drag bucket, right? And let us see how CD varies with angle of attack. So this is 0, at angle of attack 0 you have CD, and CD increases with angle of attack on either side, right? So this particular point is CD when alpha is equals to 0. Right. This is not CD naught. CD when alpha is equals to 0. So you have to be careful about using this CD when alpha is equals to 0, CD when CL is equals to 0. Let us look at airfoils. Right. We'll again get back to the drag polar. Meanwhile, let us look at various aerofoil series that are for which the experimental data is available. So NACA is National Advisory Committee for Aeronautics, have developed various series of aerofoils, and they have tested these aerofoils for different Reynolds number, right? So the data for CL variation with angle of attack, CD variation with angle of attack, as well as the pitching moment coefficient variation with angle of attack is available, right? Now ultimately what we want the wing to generate is sufficient lift, right? Sufficient lift to overcome the weight, right? Now the plan form you will decide from the mission requirements, but you need to select the corresponding cross section as well, right, called aerofoil selection. What we will do in this course is we will try to see what is the design CL, and from there we will try to get to know what is the CL alpha of this wing, right? From this CL alpha of wing we will try to figure out what should be the aerofoil characteristics, what should be the CL alpha of aerofoil. So to understand what is CL alpha of aerofoil, CD naught of aerofoil, right, and CM alpha of aerofoil, or CM about aerodynamic center of aerofoil, so we need to understand various series that are available, right? So let us first consider a NACA 4 series aerofoil, which is a famous example, right? NACA 2412, where the first digit 2 talks about maximum camber in hundreds of chord, that is equals to 2% of chord, or percentage of chord, 0.02 of C. Let us say if you consider an aerofoil, say this is my aerofoil. If this is a NACA 2412 aerofoil, then let us say if this is 1 meter chord, then the maximum camber that I have is about 20 centimeters, right? And the second digit 4 represents the location of this maximum camber. In tens of chord, or location you will get when you multiply this second digit by C by 10, that is equals to 0.4 C, right? Approximately at 40% of chord. This maximum camber will present approximately at 40% of this chord, right? Say this is your chord, line joining leading edge and the trailing edge, and say at 40% you have this maximum camber. And last two digits gives the information about maximum thickness of a 4-digit aerofoil. Maximum thickness in percentage of chord. That equals to 12 divided by 100 into C, 0.12 C. Is that 12% thick? So if you have 1 meter chord, you will have 12 centimeters thickness, right? All you can get is maximum thickness of 12 centimeters. So you can design your spar accordingly. And say if you want to accommodate a fuel tank in the wing, or if you want to accommodate batteries in the wing, then you have to keep a upper cap on the battery size or the fuel tank size. NACA 5 series airfoil. So example is NACA 23012. So the first digit here, 2, first digit, gives the information about maximum camber in percentage of C, that equals to 2 by 100 into C, 0.02 C. So the first digit will also talk about design CL, right? So CL design is the design lift coefficient, is equals to 2 multiplied by 3 by 2 into 1 by 10. So 3 by 2 into 1 by 10, right, is a factor that you need to multiply with this first digit of this 5 series airfoil to get to know about what is the design CL of this airfoil. And now 30 represents the location of maximum camber. So these two digits together, location represents location of maximum camber multiplied by 1 by 2 into 100, 1 by 100, right, multiplied by 1 by 2 to 1 by 100 of chord. So the location of maximum camber for this example is 30 into half 0.15 C. So if you consider a meter, if you consider chord as 1 meter, that is 1 meter airfoil, then the maximum camber lies at approximately 15 centimeters from the leading edge, right? And last two digits gives you the information about maximum thickness. In percentage of chord. Okay. That is C by 100. So the maximum thickness is 12% of C. Right. Now there is another series called 6 series airfoil, also known as laminar series airfoil. So example is 65418. Okay. So you also find some other digit as a subscript, right, for this kind of airfoil. So let us see what is the significance of the subscript here. Now the first digit 6 simply denotes the series of airfoil. That means this airfoil belongs to 6 series, like 6 series of airfoil, right? And 5 denotes the minimum pressure location of minimum pressure in tens of chord. So the minimum pressure when the flow is completely attached will be at 0.5 C bar or C. 5 by 10 into C is a 0.5 C. Four talks about design CL, design lift coefficient, sorry, in tens, right? So design lift coefficient in 10, that is 0.4 is the design CL of this aerofoil, and 18 here talks about maximum thickness in percentage of chord is equals to 18 by 100 into C. So it is approximately 18% of chord. Maximum thickness for this aerofoil is 18% of chord. Now what does this subscript denotes? Right. What is the significance? So we have design CL, right? Say if this is CL, coming back to this drag polar, CL and CD, variation of CL and CD. Right. Okay. Now, say this is my CL design. In this case is about 0.4. This is the CL at which I need to fly. Yeah, we'll talk about this design CL in the coming lectures, right? So, but assume that this is the CL at which I need to fly, right? If I fly at a particular velocity and with this CL, right, I'll be able to generate enough lift. That's the understanding of what enough lift to sustain the weight at that particular altitude. So that's the understanding of this design CL for the time being, right? Let us keep it up to that. Now, so this design CL is achieved at a particular angle of attack. We know CL is expressed as CL naught plus CL alpha into alpha at that particular angle of attack. So say if you somehow if you change the velocity, right, due to maybe a headwind or tailwind, suddenly the aircraft velocity or the UAV velocity is changed. So because of which you need to again increase or decrease the CL depending upon the type of disturbance, right? Or the CL has to be changed, right? So you need to either trim at higher angle of attack, bit higher angle of attack, or bit lower angle of attack to achieve the respective CL, right? But this particular series of aerofoil, if you look at this particular series of, even though if you change your design CL to a limit, no, to a small within a small vicinity, this CD will still remain same, almost constant, right? So that particular regime where the CD remains constant with even the CL changes or the alpha changes is known as drag bucket. So here in this case it is like 0.4 is your design CL. Now, so say this is your 0.4. Now 3 here, 3 by 10 is what? 0.3, right? 3 multiplied by 10, 1 by 10, which is 0.3. Like, so you have CL design plus or minus 0.3. The CD remains constant. CD remains almost constant. So 0.1 to 0.7 of CL, the CD almost remains constant here for this particular. So this is the significance of this particular digit, right? So don't you find it interesting? Like you can increase L by D without increasing the drag. That means you can trim at higher angles of attack.